Hi, and welcome back. This is the first of three videos for Chapter 5. Now, Chapter 5 starts us on our journey into the study of electricity and magnetism. Now, that said, you might find it beneficial to go back and review vectors and things like that from your University Physics 1 class because we're going to be using a lot of vectors not only in this chapter but also in future chapters and also through our discussion about magnetism, which will take us towards the end of the semester. Now, that said, we're going to start with the study of electricity. Excuse me. So, electricity gets its name from a gemstone that the early Greek called electrum. Now, electrum actually is fossilized tree sap. We know it as amber. And, you know, uh, if you remember University Physics 1 and my brief discussion about how the Greek viewed um, their physics back then, they were very interested in things that caused forces. So, one of the things they realized was that if you took a piece of electrum and you polished it with wool, say, in order to begin to shape it, bits of the wool would actually be attracted to and would stick to the electrum. So, this in itself was a new and unique effect, and so the study of that effect, and the properties of electrum were called electricity. Now, that said, um, before we really start to get into this, let me just lay out a few things that over the years we learned about electricity. The first thing is that you can use, or at least you can induce through static effects, like for example, laying on a trampoline on a cold day and moving your arms back and forth on it, you can feel the static electricity, such that things can attract and things can repel. So, the fact that you can attract and repel implies that there are potentially two polarities. Now, we know those as positive and negative. When we talk about magnetism, what we'll discover is that there are two polarities of magnetism, north and south. Basically, just two different things, such that positives affect positives and negatives affect negatives in order to cause repulsion, and positive affect negatives to cause attraction. Hence the worst dating advice ever: opposites attract. Now, we also know that whatever this electrical effect is, this force that's generated, it acts over a distance. So, unlike, for example, taking and opening a door, or pushing something across the table, these are two effects that are consequences of contact. This is a lot like gravity in that it acts over a distance without some sort of clear connection. Now, it also turns out that not everything is affected. So not everything is subject to this electrical force. Now, lastly, the force itself seems to go like 1 over the distance squared. Okay, now this is called an inverse square force. And we actually have talked about an inverse square force before, and that was the force of gravity. Now, that said, uh, as we got better and better and better at doing science, and as our equipment got more and more exact, what that did was to enable us to ask questions about this electrical force. First of all, the property that is positive or that is negative with respect to an object is called charge. So the two polarities, the positive and negative polarities, are examples of two types of charge. And not only that, you know, we can ask the question, is there a smallest amount of charge? Now, this is actually a pretty smart question to ask. Like for example, if you've ever had chemistry, you know a little bit about chemistry. You know that there are these things that are called atoms, and that by definition, an atom is the smallest amount of a substance that retains all of its properties. Okay, which incidentally was originally an idea that came from the Greek, specifically a Greek philosopher named Democritus, who used an apple to deduce the existence of the atom. A good 2,000 or so years before we were actually able to directly detect them. Now, that said, you can ask the question, is there an atom of charge? And it turns out the answer is yes. And there was a person named Millikan who performed an experiment that was called the oil drop experiment. And it turns out, see, what Millikan was doing was he was hunting to see if there was some sort of atom of charge. I'm not going to go into the actual experiment itself because we have a tremendous amount of stuff that we need to cover in this particular chapter. Suffice to say that the purpose of the experiment was to deduce as to whether or not there was an atom. And what he discovered was that there was a smallest amount of charge below which he didn't see values of. That amount is about 1.6 times 10 to the minus 19th, what we call coulombs, abbreviated C. This is the unit of charge. Now, we know that we use the letter M for mass. We use, for example, the letter L for momentum, or angular momentum, P for momentum or pressure, what have you. We actually use a lowercase q generally for charge. Now, the unit itself, the coulomb, gets its name from a scientist who did a lot of work with electricity and magnetism and actually deduced the proper form for the electrical force, which we'll be getting into here in a bit. That said, we know, from a modern standpoint, that this value of charge, this 1.6 times 10 to the minus 19th coulombs, is the charge of the electron, which would be negative. It's also the charge of the proton, which would be positive. Now, we know that, all regular matter that we're at least familiar with is made fundamentally out of atoms. And atoms themselves consist of electrons and protons, and also potentially neutrons, which we think of a neutron as having a charge of 0, which is true overall. Neutrons are actually composed of 3 particles that are called quarks. Quarks are what we call fundamental particles. They're fundamental. By fundamental, I mean that they are building blocks. You cannot break a quark into smaller pieces. A quark is the smallest part of what you make a proton out of. Now, electrons are also fundamental particles. We don't construct other particles out of electrons other than things like atoms, obviously. But you, as best as we can tell, you can't break electrons into pieces. These are fundamental as well. So protons themselves are not fundamental. They're made out of 3 particles. Neutrons as well are made out of 3 particles. 3 quarks for the proton, 3 quarks for the neutron. For a proton, each quark has a charge of 1/3 of 1.6 times 10 to the minus 19th coulombs. For a neutron, you have a plus 1/3, a minus 1/3, and a quark that has a charge of 0. This is actually how we're able to detect neutrons. Most of our particle detectors operate off of trying to detect some sort of charge. A neutron may have no net charge, but since it is composed of things that are charged, it has regions of what we call polarity, which we'll be talking about momentarily. Now, as I had mentioned earlier, specifically right here, where not everything is affected by this charge stuff, um, that implies the existence of things that are affected. Things that are affected by charge many times fall up under the idea, or at least up under the header of conductors. Conductors allow the transport of charge. We're going to talk about why that is here in a moment. And then you have things that do not allow the transport of charge. Those are called insulators. Do not allow the movement of charge. So, that said, one question you may have is why is it that conductors allow charge to move? And it has to do with the fact that most conductors are metals. Now, I know some of you have not had chemistry, so I'm going to sort of make this as clear and as easy as possible. I want you to think of this as a whole bunch of nuclei, like you know atoms, the center of an atom, the thing that contains the proton and the neutron. Um, so those are all nuclei, and then we think of, in what turns out to be an entirely incorrect way, um, the electrons as sort of flitting around um, the nucleus of the atom. So let me draw little orbital paths here. Oops. That way. So here are a bunch of little orbits right here. I'll just use the last one. There we go. So these are all like the boundaries of the orbits, right? Now, so so we have these little electrons, and there may be many of them. We'll say two right here, like this, just on the outside. For those of you that have had chemistry, you know that atoms have shells, and on the shells, that's where your electrons live, et cetera, and so on. And but it turns out that on the outermost part of your atom, the outer shell, we say, uh, in a conductor, specifically in metals, these electrons are sort of free to move. So these guys can jump like this, from atom to atom on the outside, like that. So it's these free electrons that allow the movement of charge, because 99.99 times out of 100, what's moving in a situation like this are the electrons. The positive charges are locked in place inside the nucleus. So, for example, in a wire which might transport electricity, what's flowing through the wire is not the positive charge, because those are locked in place since your wire is a solid. So it's holding its shape. But it's the actual electrons on the outside that are moving. Okay, those are the things that are flowing. So insulators do not have free electrons that are able to move. And incidentally, a conductor may have one, two, or more free electrons. Now, there are other things as well that can support the passage of electrical charge. For example, if you take a gas and you superheat it, you get it so hot that you break it up into its original components, a nucleus and say some electrons and stuff like that. You can have flow in that, and typically the flow is also electrons as well. Now, so that said, I want you to think of an experiment here. So what we're going to do is we're going to take a piece of cork, perhaps, and what I'm going to do is to take something that has a positive charge. Now, how do you get a positive charge on something? Well, for example, a piece of plastic, which would be an insulator that you can also induce charge onto, has can have a charge on it, because what you do is you rub electrons off. So you're taking electrons off of it. So remember, the positive charges are locked on the inside, in the nucleus. Those things aren't free to roam around. It's the electrons that you can take and you can move pretty easily. So, maybe here's a rod of plastic that you've managed to charge up. Maybe you've given it a positive charge, we'll say, like that. And what you do is you get this thing close to it. Now, if you remember the properties of our force, like charges repel, opposite charges attract. This force acts over a distance. Not everything is affected, and the force looks like 1 over the distance squared. So here, when I get this positive thing close to this piece of cork, any negatives that are sitting inside here that are free are going to want to be attracted to it. So overall, this thing originally is neutral. It doesn't have a charge on it. But what you have is you have the negatives here sort of being pulled towards the positive here. And what that does is to leave a sort of a void of negatives over here. So this side right here is overly negative, and this side right here is overly positive. But if you were to add how overly they are together, you get a net 0 charge overall. Now, so what I've done by separating these things is we say that we've polarized it. Okay? So if you remember earlier when I was talking about the neutron and how it's made out of a positive charge, a negative charge, and a quark that has a 0 charge, we detect the polarization of the neutron. That's how we're able to detect neutrons. Now, if you're in chemistry, that's also generally what polarization means, is that you have regions in which they're overly positive, you have regions in which they're overly negative, but when you add the positive to the negative, what you do is you have 0. So now what I'm going to do here is to move this thing away. I'm going to let these things go back to normal. So now this thing is back neutral. The electrons have now been attracted back to their positives, and everything overall is nice. And what I'm going to do now is I'm going to hook my piece of cork to a wire that allows charge to move. And I'm going to put this in the ground. Okay, so I'm going to maybe take and drive a rod into the ground and tap it in there. The symbol for ground that we use basically are lines like that. It's in the ground. So this is attached to the ground. Now the ground is a tremendous reservoir of charge. Overall it's neutral, but it's a source. So what I'm going to do is I'm going to take and get this close to it again. What's going to happen is you're going to have negatives pulled towards it, and you'll have a glut of positive over here. But the thing is the positives over here are going to take and attract any negatives that are free here up the wire into it. Okay? So what I've done is I've actually made this thing overall very negative. Then I'm going to unhook my wire. So now I've broken it, broken the connection. There's no way that the electricity can flow through it. Okay, and then I'm going to move this away. And what you'll discover is that your piece of cork now has a negative charge. This is called charge induction. I've induced or compelled this thing to have charge on it by getting something else close to it that has charge and just making sure it's connected to a reservoir of it so it can flow into it. Okay? Now, incidentally, a configuration where you have a bunch of positives over here and a bunch of negatives over here. If you just have one positive region, one negative region, you can call this a dipole. Remember monatomic, diatomic gases, this is 2, it has 2 poles. One region that's negative, one region that's positive. But when you charge this by induction, there's just negative here. Now, that said, earlier I had mentioned the unit of charge is the coulomb, and I said that there was this guy named Coulomb who had done a lot of work with it. So Coulomb actually had done work looking at how charges attract and how they repel and how that force changes over distance. And he came up with something we call Coulomb's law. So I want you to imagine two things that have charge. So maybe here's two metal spheres. This has charge of Q1. This has charge of Q2. And they're separated by a distance of r, like this. What Coulomb discovered was that if you look at the amount of force that's felt between them, that this force is proportional to each charge that's there. Okay? So if you increase the amount of charge here, the force gets bigger. If you increase the amount of charge here, the force gets bigger. If you increase both of them, the force increases as well. And it's a linear relationship. He also discovered that the force itself affects things like 1 over the distance squared. Now, if you put this together, what you have for your electrical force is something that depends upon the charge of both of the things involved and the distance between them squared. Okay? Now, Coulomb originally found a constant of proportionality that we call kappa, okay, or K, Q1, Q2 over R12. R12 is the distance between them. Now, Coulomb's constant, which is what this is, has a value of 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Okay? But many times this is written differently. Many times we write K as 1 over 4 pi times a constant that's called epsilon naught. Now, epsilon naught is called the permittivity of free space. The 4 pi is there because many times we do geometry with it, calculus, and because of the geometry that's involved, there end up being factors of pi. Many times it's a spherical geometry, and there's a factor of 4 pi, and that just allows for easy cancellation. And you'll have to constantly carry around 4 and pi. So epsilon naught has a value of 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. So the way we're going to use Coulomb's law is using the 1 over 4 pi epsilon naught. But just be aware that, kappa is just as valid here. Q1, Q2 over R12. This is the magnitude of it. Okay. Now let's talk about how it works as a vector. If you remember gravity works through the center of things. It turns out that that Coulomb's law looks the same, basically. So if you were to think of two charges, I'm going to call this charge Q1 and this charge Q2. This is the distance from Q1 to Q2, which I'm going to call R vector 1, 2. Okay. The force between them as a vector would look like 1 over 4 pi epsilon naught Q1, Q2 over R12, that's its magnitude, times R hat 1, 2. That is the unit vector that points along the radius from the center of one to the other. Now, frequently, I will be doing things like this. Perhaps, for example, your charges are here. Relative to my origin, these are the locations of my two charges, Q1 and Q2. But the force itself only depends upon the distance between them, which I'm going to use a different color as this right here. Now, so I'm going to call this right here R12. This right here is R1. This right here is R2. Now, if you remember vector addition, this plus this is equal to this. So, R12 is equal to R2 minus R1. So many times you see this written that way as well. This is squared, by the way. I want to make sure I squared it over here. Nope. Sorry about that. That's squared. So, so that said, let's talk about this unit vector right here. Well, the unit vector points from here to here, and a unit vector has a length of 1. Okay. So one way that you could take and you can make a vector have a length of 1 would be that if you took that vector, which we'll call A, and you divide it by its length, which looks like this. So this you could call a unit vector. So here you can actually write R12, the unit vector, as R2 minus R1 divided by, we're going to use 2 bars here just to be consistent, R2 minus R1, its length, whatever that is. Okay? So in some more complicated examples, I'll bring this up again, but you can also see Coulomb's law written the following way. We say it's cubed because you have 2 of them here, and then you have a third one here. Because remember, this is a magnitude. All right? So let's just do some simple examples here. How much force is felt between 2 point charges, each of which has a charge of minus E? E is the charge of the electron, 1.6 times 10 to the minus 19th coulombs, that are separated by 10.0 nanometers. So 1 nanometer is 10 to the minus 9th meters. Okay. So let's draw a picture first. So here's charge 1. Over here I'll say is charge 2. The distance from here to here is 10 nanometers. Okay. When I say how much force is felt between the 2 point charges, I'm asking for the magnitude. So The reason why is because um, we know, as per Newton's third law, that if object A exerts a force on object B, B exerts the same force back on A, just in the opposite direction. So the magnitude of the force is going to be that both of these guys feel are going to be the same. The direction is going to be different. In both of these cases, you're dealing with a negative charge. So here, since you have like charges, they're both negative. They're going to want to repel, push each other away, which means Q1 will experience a force this way, and Q2 is going to experience a force this way. So the directions of the forces are going to be a little different, but the magnitude, that is how strong the force is here and how strong the force is here, that's going to be the same. So what we're given here is that Q1 and Q2 both have a charge of minus E, which is minus 1.6 times 10 to the minus 19th coulombs. Now, the separation distance, which I'll call R12, is 10.0 nanometers, or 10.0 times 10 to the minus ninth meters. And what I'm trying to find here is the force F. So like I said, we're just going to deal with magnitudes here. So my force F here is going to be 1 over 4 pi epsilon naught Q1 Q2 over R12 squared. Now I'm going to put absolute values around Q1 Q2 because we're just asking for the magnitude. In the event that we were dealing with opposite charges, one of these would be negative, one of these would be positive, which would put a minus sign out in front. And we know that lengths of vectors, which are the magnitudes of vectors, are always positive because they're lengths. So I'm just going to enforce that, even though technically here the negative times the negative would give us a positive. So if I plug the numbers in here, I have 1 over 4 pi. Epsilon naught, let's see, is 8.85 times 10 to the minus 12th coulomb squared per Newton meter squared. So that's just the constant out in front. And then I have 1.6 times 10 to the minus 19th coulombs. There are two of them. It's the positive value. That's the reason why I didn't put a negative sign there. So there's two of them. I'm going to square it. And the distance here is 10.0 times 10 to the minus ninth meters, and that's squared as well. That's the length. Okay, so when you do this, let me put this into my calculator. So there's that divided by 4 times pi times 8.85 times 10 to the minus 12 times 10 times 10 to the minus ninth. I gotta square that. And I get hold on, no wonder. So that number didn't look right. I put a minus 19th and not ninth in the bottom. So let me delete that and do it again. Okay, that looks better. All right, so the force itself is very small. That's 2.3 times 10 to the minus 12th newtons. And you can check to see if it's newtons. You've got 2 coulombs here, which are going to cancel out with these. You have 2 meters here, which are going to cancel out with these. And this is going to flip up to the top to give you newtons. So how much is it? 2.3 times 10 to the minus 12 newtons. Okay. Now let's do another example. What is the force felt by the electron in a hydrogen atom which has an orbital radius of 53 picometers? Now, a picometer is very tiny. It's like 10 to the minus 12th. So a pico is 10 to the minus 12th meters. Picometer. So what we have here basically is, here's my coordinate system. Here's y, here's x. Here is my proton at the center, right there. And then here's my electron, we'll say, going around over here in a circle. And then this right here is my vector, R12. So what's going to happen is, you know, my electron here, since it's negative, and, you know, the charge of the electron is minus 1.6 times 10 to the minus 19th coulombs. It's being attracted to the proton here because the charge of the proton is the same as the electron. It just has a positive sign. So that's the force that's providing the centripetal force that allows this thing to go around in a circle. Okay? Now, our radius here, which I'm going to call r, this right here is equal to something that's called A naught. A naught is 53 picometers. A naught actually is a constant. The radius of the hydrogen atom is something that we use to scale atoms in general. So this would be 53 times 10 to the minus 12th meters. So this is a given. We also know, again, the charge of the electron, minus 1.6 times 10 to the minus 19th coulombs, and the charge of the proton, which is 1.6 times 10 to the minus 19th coulombs. Now what we're trying to find here is the force on the electron. Okay? So Coulomb's law, the version that I'm going to use here, is 1 over 4 pi epsilon naught Q1 Q2 over R12 squared r hat. R hat, again, points from the center outwards. So r hat, or R12, you know, since we're placing the proton at the center, okay, and this is going around it, the length of its vector is 0, which means we're just dealing with r, which is, you know, just pointing to where the electron is. So we can drop all the 1,2s here. I'm going to call this F sub E. Charge of the proton, charge of the electron over r squared r hat. So now let's plug some numbers in. And this is what, 8.85 times 10 to the minus 12th Newton, or actually that's Coulomb squareds per Newton meter squares. QP is 1.6 times 10 to the minus 19th coulombs. QE is minus 1.6 times 10 to the minus 19th coulombs. And then our distance here is 53 times 10 to the minus 12th meters, and you have to square that. So if you do the numbers here in the calculator, so 1.6 times 10 to the minus 19th times 1.6 times 10 to the minus 19th, but negative. Let me insert that there. Divided by 4 times pi times 8.85 times 10 to the minus 12th times 53 times 10 to the minus 12th. I'm going to square that. I end up with a negative 8.19 times 10 to the minus 8th newtons r hat. Yeah, there's an r hat way over here. So the force itself is inwards. It's a central force. It's making this thing go around in a circle. Okay? Now, so, that said, we can talk about what happens when you have more than just two charges. Okay? So we're going to call charge Q the one that we're interested in finding the force on. Q1, Q2, Q3, all the way out to Qn, all these other charges. These are the ones that we're going to be looking at exerting the force onto Q. So just like, any other situation dealing with forces, if I place the thing that I'm interested in finding the force on here at the origin, I'll call that Q. And I'll look at all of these other charges that are sitting around. I'll call that R1, R2, R3, R4, R5, and so on. You got all these charges that are sitting around here. Q1, Q2, maybe Q3, Q4, Q5, R1, R2, R3, R4, R5, and so on. Then, for example, if I looked at the force of Q1 on Q, I'm going to call that F1, the force of Q1 on Q. That would be 1 over 4 pi epsilon naught Q1 Q over, I'm going to call that distance there R1, okay? There. The second one, 1 over 4 pi epsilon naught Q2 Q over R2 squared, R2 hat. All the way down to the last one. Which looks like that. So the net force, which I'm just going to call F, which is what you get when you add up all of these individual forces. Since they all have Q in common, I'm going to pull that out in front, and it's going to look like this. So you can sum these things. And not only can you sum them, we know that if you have enough of these things, you could turn what would be a discrete number of charges into an infinite number of charges and make it an integral. Now we'll be doing that in our next video. But this right here, we're going to discover also in that video, we call the electric field. But the point is that you can sum these things. Now the act of summing vectors up like this is called superposition. And I'm going to be using this word a lot. Okay, so just realize that when I say superposition, I'm talking about the act of adding vectors together. Okay? Now, that said, let's do a more complicated example that deals with something similar to this. And so what I have here is I have four charges. Okay, they sit on the corners of a square. So you have a 2 microcoulomb charge here, a 5 microcoulomb charge here, a 4 microcoulomb charge here, a minus 3 microcoulomb charge here. Now, just for reference, 1 microcoulomb is equal to, this is 10 to the minus 6 regular coulombs, okay, from a conversion standpoint. And what I'm interested in is finding what the force is on the minus 3 microcoulomb charge, this guy right here. Okay, I want to find out what the force is here. Okay, now look. If I look at 5 microcoulomb charge and 3 microcoulomb charge, we know opposites attract. So what's going to happen is the force here on that one is going to want to pull the minus 3 microcoulomb charge that way. So I'm going to call this F1. So this is number 1. Here, a positive charge and a negative charge, pulling it straight this way. I'm going to call this one right here number 2. And this right here is F2. Likewise, a positive charge here and a negative charge here. F3. This is number 3. Okay? Now, this is a square. Each side of the square has a length of 10 centimeters. I'm going to call this L. Okay? So what we've been given here is that our charge Q, the one that we're interested in, is minus 3 microcoulombs, or minus 3 times 10 to the minus 6 coulombs. The first charge, Q1, is 5 microcoulombs, or 5 times 10 to the minus 6 coulombs. Our second charge here, Q2, is 2 microcoulombs, or 2 times 10 to the minus 6 coulombs. Our third one is this one right here, 4 microcoulombs, or 4 times 10 to the minus 6 coulombs. We also have sides of length L, which is 10.0 centimeters, or 0.100 meters. We're trying to find the force on the minus 3 microcoulomb charge. Now, so if you remember University Physics 1, we have 3 forces at work here, which means that, it'd probably be a good idea to draw a force diagram. So here's our force diagram right here, centered on our charge Q. We have a force that goes up like this. Let me draw that a little bit better. A force that goes up like this. A force that goes this way. And a force that goes this way. This is F1. This is F2. And this is F3. Now, what's our angle here? We'll take a look. This is a square that has sides of length L, which means that this is 90 degrees. But these sides have the same length, which means that this angle right here is the same as this angle right here. Now we know the interior angles of a right triangle sum up to give you 180 degrees. So if this is 90, then this plus this would also need to be 90, which means that each one of these angles right here are 45 degrees. I'm going to call this theta. Okay? So this is y, this is x. I'm going to sum up my forces to get the net force. Which I'm just going to call F. 1, 2, and 3. Now, let's talk about what's going on in the x direction. In the x direction, I see that my third force here, F3, lies entirely in the negative x direction. So Fx here, the x part of my net force, is going to be minus F3, and then the x part of F2, which is also negative. Now, we're going to fill in what this is here in a moment. In the y direction, I have a positive F1. I also have a positive F2y. Okay. Now let's talk about what F2x and F2y are. We have an angle that looks like this. This would be F2, this would be F2x, and this would be F2y. So here, F2x is going to be the adjacent side, which is cosine. And the y part is going to be sine. So, it looks like this. Okay. Now, so what do our vectors in magnitude look like now? Because we've already taken into account the directions. So if we've already taken into account the directions, whether we're dealing with opposite charges or like charges doesn't matter anymore, because we've already figured out what the differences in polarity are going to do for us. So when we plug things in, we're going to just be plugging the positive values in. Okay? So here, for example, F1, which is the force of our first charge, okay, on our main charge, is going to look like this. 1 over 4 pi epsilon naught Q1 Q over L squared. Since that's the distance between here, that's its magnitude. Okay. F2 is a little more complicated, because remember, our force acts from the center of one charge to the center of another charge. That's along this direction right here. So if you think of this as a triangle, we have a triangle that has a side of length L, a side of length L, and we're trying to find the hypotenuse. Well, we know the hypotenuse, this distance right here, which I'll draw as a dotted line like this. We know that distance right there is going to be L squared plus L squared, the square root of, using the Pythagorean theorem. The hypotenuse squared is equal to the sum of the square of the sides, right? So what that means is that in the bottom, our hypotenuse here, this distance, which I'll call R2 just for the moment, this is R2 squared here, which is going to be L squared plus L squared, or 2L squared. So now we're dealing with Q2 affecting Q, and the distance squared between them again is 2L squared. Now, F3, that's this one right here. Okay? 1 over 4 pi epsilon naught Q3 Q over L squared. Okay, so now it's just an issue of adding the components together. So Fx, for example, we know is minus F3 minus F2 cosine of theta. If I put in what minus F3 is, that's going to be minus 1 over 4 pi epsilon naught Q2 Q over L squared. Then we have a minus F2. F2 is 1 over 4 pi epsilon naught Q3 right there. Sorry about that. Q2 Q over 2 times L squared. Then we have the cosine theta there. Now, Fy is F1 plus F2 sine of theta. F1 is 1 over 4 pi epsilon naught Q1 Q over L squared. F2 is 1 over 4 pi epsilon naught Q2 Q over 2L squared. And then you have the sine theta. So these are our components right here. And as you can see, they actually simplify a little bit, as in you can pull a bunch of stuff out. For example, both of these terms have a minus sign in front. There is a 1 over 4 pi epsilon naught in front of both of them. There's also a Q over L squared there. So what you're left with after that is a Q3 plus a Q2 cosine of theta. Likewise here, a bunch of common terms. 1 over 4 pi epsilon naught. They both have a Q. They both have an L squared. Oh, this term right here has a 2 on the bottom. And here, they're added together, obviously. So it's going to be Q1 plus Q2 over 2 times sine of theta. So there you go. We have, both of our components. So, for example, with respect to fx, if you plug your stuff in here, that is 1 over 4 pi epsilon naught. Epsilon naught is 8.85 times 10 to the minus 12th coulomb squared per Newton meter squared. So that's that one right there. And then you have a Q. Remember, it's the absolute magnitude of Q. And Q itself is 3 times 10 to the minus 6 coulombs. So that's Q. You have an L squared here. L, if you remember, is 10 centimeters or 0.100 meters. That's squared. Then you have Q1 plus Q2 over 2 times cosine of theta. Q1 is 5 microcoulombs. Actually, rather that was Q3 plus Q2 over 2 cosine of theta. Q3 is 4, and Q2 is 2. So this is going to be 4 plus, and then our angle is 45 degrees. So that takes care of the first one right here. Q3 plus Q2, again, Q3 is this, Q2 is that. So if you actually plug your numbers in here, you get, let's see here, 1 divided by 4 times pi times epsilon naught, and times 3 times 10 to the minus 6 divided by 0.1 squared times 4 times 10 to the minus 6 plus 2 divided by 2 is 1. And then cosine of 45. And let me make sure my calculator is in the right mode. It is degree mode. So when I do this first term right here, I get 12.698 newtons. So let's do the second one. Let's do Fy. Again, this is positive, by the way. 1 over 4 pi epsilon naught. So there's that. 3 times 10 to the 6 coulombs again over 0.100 meters squared again. So that's, yeah, same stuff, you know, that sits out in the front here. Yeah, same stuff. It's just got a different sign. And now it's Q1. Q1 is 5 times 10 to the minus 6 coulombs. The next one is Q2 over 2. Q2 again is 2 times 10 to the minus 6 coulombs. And then now you have a sine of 45 degrees. So if you do this, let's see here. I get a positive 15.395. So the x part's negative, the y part's positive, which is exactly what we expect in our picture here. So what's my overall force look like? Well, my force in magnitude is just going to be the square root of the sum of the squares. And if you do that, uh, 698 squared. Let me take the square root of that. I get 19.956-ish newtons. My angle, which I'm going to call alpha, that is, it's going to, based off of what I see, it's going to be longer along y than along x. So my vector here for my net force is going to be up here somewhere like that. So I'm going to call this angle right here, like I said, alpha. So so if I think of this as f right here, and this is fx, and this is fy, and this is alpha, then this is going to be the inverse tangent of fy over fx, or 15.395 newtons divided by 12.698 newtons. I'm putting in the positive value because as drawn it's a positive angle. So the inverse tangent of 15.395 divided by 12.698, and that's 50.48 degrees. So one way I could write this would be that my force here is, looking at the number of significant digits I have here, I have 1. These are all 1. And then I have 3 there, so we're going to keep it 1. So looking at the sig figs, it looks like it's going to be 20 newtons, making an angle of 50 degrees with respect to the negative x-axis. Or I could just do my substitution here, or my subtraction rather, and call this alpha if I wanted to, which would be 180, obviously, minus 50. So that would be 130 degrees. So either is fine. Okay, so this, like I said, introduces us to Coulomb's law. And in the next video we're going to take a look at the electric field, which it turns out, believe it or not, ends up being far more important than just the force by itself. And I'll see you then.